Have a good New Year. So I'm excited to introduce you Dr. Laura Ruiter. Laura is a research assistant professor from Tufts University. She's working on this project at this moment, but before she joined Tufts, she's a developmental linguistic. So she's trying to bring how young kids acquire language to inform us how they can learn computer programming better or computer science better.
Absolutely.
Thank
you so much, Jen. Thank you. I hope everyone can hear me all right. I'm really excited to be here. As Chen just mentioned, this is a new project for me. My background is in developmental linguistics and psycholinguistics and language processing. But as I'll show you today, and that's what my argument will be, is actually that we can bring those two disciplines, early computer science education and the study of language development, together to learn more about it. But before we get started, I'm just curious, maybe just by a show of hands, how many of you have used or are using C or C++? How about Python? Ooh, okay. Language of choice. MATLAB? Also quite a few. And R? All right. Some people multiple times, yeah. So maybe... Sorry, limited space, Fortran. Yeah, to be honest, I've never done Fortran, so I can't say anything about it. But even more, there are more languages, I'm sure. But maybe now you think, okay, if we're here at the university, you're all scientists. Of course, you know how to program, how to code, because you need it for your research, you need it for your work. But we also know that in today's computer-based world, it's actually not only scientists who need to know how computers work. There is a push towards computer science education from early on. So people have said, well, nowadays everything is computers. Kids need to learn this from an early age. But there's a lot of argument going on about how to do this best, because it's relatively new, right? We've had literacy education for a long time, science education, math. I mean, there are changes, but these have been disciplines and subjects in schools for a long time, right? This is relatively new. And today I'm going to argue that we need to see computer science through a different lens. So not as something that is a totally different subject or discipline, but something that is an integrated and integral part of a well-rounded modern education. So I'm going to talk about these points today. First, as usual, when you do something, you point out where the issues are, and I'm going to point out where we think there are current issues with early computer science education. Then I'm going to talk about where computers actually play already a role in children's lives. So I'm going to talk about something called computational thinking. Then talk about the parallels between coding and natural language, which is what I'm super interested in. And then I'm going to introduce to you the programming languages that our research group, our lab, together with others, has developed, called Scratch Junior and Kibo. Kibo is a robot. You can already see it over there, and I hope if we have the time, I can give you a quick demo later on. And towards the end, I'm then going to introduce the coding as another language curriculum, a kind of concrete application of this idea to bring together language and literacy development and computer science. Okay, problem with early computer science. You're all probably familiar with graphs like this that we find in articles, right? So we say, there's a big problem. We have like so many programming jobs, but only so many computer science graduates. So there's a big gap in the labor market. Or the other thing is, well, we're talking all about STEM, but actually most of the jobs in STEM are in computing. And then say, but only 10% of STEM graduates are actually computer scientists. So the way that this is framed, and this is not wrong, of course, this is a fact, or these are facts, but the way that it is framed is that computer science is a job, right? And also computer science is only part of STEM. It's seen as it's inclusively part of STEM. And the main argument push that we hear in the media is it's important to have a strong and competitive programmer and engineering workforce, right? So America needs to compete in the global economy. But maybe I'm preaching to the choir that education, science education in general, is crucial, and not just for workforce development. We see it as something that we want children to learn and understand things that they need also in everyday life to be, as citizens. So this is the point that we are making, is saying this is all true, but it's a little bit of a view that is too much just focused on the idea of workforce development. Now, as I said, there has been a push, and there are more and more states that are trying to introduce computer science in the early years. And there are some great initiatives out there. This is an example from code.org. And I have to say the organization does great things to promote coding and computer literacy. But this is a typical, they have like online courses that teachers can use to do coding with kids. And as you can see, this is more of a set problem. So for example, the idea is this little character called Laurel, and it says, help Laurel get all of the treasure along this path, right? So starts here and has to get here, and you can kind of see the idea that you put those things into place so that the character moves along and collects those treasures. There's only one correct solution to this, right? So it's a set problem. And while problem solving is an important part of coding and programming, it's only one part. And currently, it's often framed just as problem solving. So, and I'm going to argue in the course of my talk that computer science is much more, and that we need to see what else it is in order to really make it relevant and attractive for children. So just to summarize, right now we see that computer science is seen as vocational, right? Rather than foundational. And we argue it's actually a foundation in education. It's treated exclusively as part of STEM. And the teaching focuses very much on problem solving. And that's especially for young kids, not always what they find most interesting. Computer science is so much more. So first of all, I'm arguing, and others have said that too, that computer science is actually needed for digital citizenry, right? We understand that everyone needs to be able to read and write and to do calculations to participate in society, right? We say children need to learn that so they can participate in society. Well, the same is actually true nowadays for aspects of computer science. Then, as I will show, computational thinking is foundational to many aspects of life, already in children's life. And coding in particular has parallels with natural languages. And I'm going to focus on these two, the computational thinking in everyday life and the parallels between natural language and coding in what follows now. So our approach is to actively exploit this computational thinking, and this is something I'm going to tell you about computational thinking. Maybe you're wondering, what does brushing your teeth have to do with computational thinking? But I'll explain. And language. Okay, so let's get to the first part. Computational thinking in everyday life. Well, of course, we're academics, we're scientists. Let's start with some definitions. We always love our terminology, we love our definitions. So here are some widely used definitions of what computational thinking is. I'll just read out maybe the first one. The thought processes involved in formulating problems and their solutions so that the solutions are represented in a form that can be effectively carried out by an information processing agent. Pretty technical, right? But for example, if you look at the one at the bottom, we see already a set of thinking skills, habits, and approaches that are integral to solving complex problems using a computer and widely applicable in the information society. So here we can already see that some people are saying, well, it kind of goes a little bit beyond. And in an overview paper, so you don't need to know if this is just to give you an idea. It's because the field is still trying to define what it actually is. So people have done this review and say, okay, what are the things that always come up in the definitions or in the frameworks? And we have things like abstraction, an algorithm, generalization, right? And many of you, if you work with programming language, say, yeah, I can make sense of that. But I'm here to talk about young kids. You're probably, this is a little bit, that takes a little bit far. So we actually have a framework that we're using called the 7 Powerful Ideas from Computer Science in Early Childhood. I'm not going to talk about all of them because that will be just a talk in itself, but I'm going to give you some examples of these. So the 7 powerful ideas are algorithms, modularity, control structures, representation, the difference between hardware and software, the design process, and of course debugging. We all know it's our favorite activity when we write code, the debugging. So I'll give you now some examples. So first of all, representation. Representation means that one thing stands for something else, right? And children have that everywhere in their life, and I understand that. They understand signs, for example, even young kids, they understand, oh, this is where the bathrooms are, right? They understand that. And here, just the kids drawing, this is representation because the little drawings represent people and the sun and the clouds. So they already understand that you can use something to stand for something else. What I've drawn stands for what's out there in the world, right? So representation is something that they intuitively understand. Another powerful idea and very important for computer science, of course, algorithms. And algorithms, again, it sounds very technical, but let's think about it. What it actually is a series of ordered instructional steps to solve a problem, right? This is how we write an algorithm. And now you're wondering, okay, brushing your teeth, let's think about it. This is actually one of the activities that we often have teachers do with their kids. Okay, let's think about it. How do you brush your teeth? I need to find the toothbrush. I need to find the toothpaste. I'll put the toothpaste on the toothbrush. I turn on the tap. I wet the toothbrush. I brush my teeth, and so on and so on. Importantly, it doesn't work if you leave any of those steps out. No water. I mean, we've all probably tried, but it's pretty awful. And doing it in the wrong order also doesn't work, right? So this is something where kids understand, okay, these are things that I need to do. They all need to be there, and they need to be in a particular order, right? So this is how we can explain the idea of algorithms to kids at a very young age, and they really understand that. A third example of computational thinking, so we talked about representation, algorithms, is modularity. And we're all taught when we learn to code, try to modularize things, right? So there are different ways that you can define it, but when we work with the children, we usually talk about it in terms of breaking down a problem into smaller tasks that can be combined to make a more complex process. Now, what's an example? An example is planning a birthday party. Again, something that all young kids are familiar with. And you talk about, so what do you have to do? You have to invite guests, have to make food, maybe buy balloons, all those things. And then you say, well, what does inviting guests mean? Well, first of all, you have to think about, who do I want to invite? I'll make a guest list, right? Then I actually have to write the invitations, and then I have to put them in an envelope, right? So again, you have one big problem. Party planning is a bit of a headache, right? One big problem that you break down into smaller parts, right? And this is modularity. So we're saying computational thinking is rooted in computer science, but it's really universally applicable. You see it in so many domains of life. And it's actually fundamental for everyone to master, as I said earlier on, just like reading, writing, and arithmetic, because you need it to function in everyday life. And our argument goes that we need to connect computational thinking in children's lives experiences to make it relevant and interesting for them, so that they see, oh, this is not some part that is kind of different from what I already experienced. It's kind of integrated in what I do anyway. Okay, so this is the first part, sort of showing how computational thinking is already there in children's everyday lives. The next part is now my home discipline, linguistics, or the relationship with linguistics, because another thing is that there are a lot of parallels between coding and natural language. I mean, of course, that's not an accident, right? The people who developed programming languages were humans, right? So they had a reason why they did it that way. But I'm going to argue that we can use that because coding and language have both similar form and similar functions. And both of these things are very useful in working with kids and making them understand what actually is happening there when they code, when they program. So let's talk about both of these in turn. So first about the similarities in form and the similarities in function. In form, we can say both language and coding are systems of symbolic representation, right? We have the use of arbitrary symbols, we have categories, and of course we have syntax or grammar, right? And I'm going to give a few examples, and feel free to, maybe in your head you come up with your own examples from the coding languages or other human languages that you know. Use of arbitrary symbols. And natural language is a big point about linguistics. We always realize that cat is arbitrary. There's nothing in the order of the sounds k, at, that gives you any hint that this means a domesticated feline, right? And this is why it's something different in other languages. What is it in Mandarin? Mao. So yeah, Mao. So, and it's Katze in German, my native language. So that's arbitrary. And we have the same in coding. So the letter sequence return in C++, right, means that you pass on the variable or value, right? Now the symbol, and now we're getting into the question of is it totally arbitrary. In Scratch Junior, one of the languages I'm going to show you later, this means that you have to begin an action. Now we can see that there's an iconic relationship. There's something that has to do with, maybe you have a flag to start, but still it's arbitrary because you could also have used the sign that we use for play, when you play a tape or something. So it's still arbitrary because they have got lots of choices. Then categories. So in natural language, we actually operate with categories, right? So I can say, I like ice cream, but I can also say I like dogs, parks, the countryside, right? I like noun, yeah? The same goes for verbs. I can say I can jump, swim, read, dream, argue. And of course, in coding, we also operate with categories. So for example, we have the difference between functions and arguments. And in Scratch Junior, as we'll see later, there's a difference between actions and characters, right? So characters can perform certain actions. And now in syntax, we all know that the grammar determines what is an acceptable sentence in any language. Like I can say, he likes ice cream, good. Cream, ice, he likes, no. You may still get the meaning, but it's not a grammatical sentence. In coding, we all know, for example, C++, you have to have the semicolon. Who of us hasn't forgotten the semicolon in a C++ statement? And in Scratch Junior, of course, we also have things like, and the same goes for Kibo, you cannot make a character disappear before you've added it or introduced it, right? And finally, for the people who are maybe a bit more geeky and are interested in recursion, another thing that is great in natural language is that we can create this infinitely long sentences through recursion. So I start with, he likes ice cream, but then I can just embed this into the sentence, she thinks he likes ice cream. And then I can just add, they said that she thinks that he likes ice cream. And he thought that, they said that she thinks he likes ice cream, right? We can go on and on and on. This is a fascinating ability that we have with language. And of course, we have that in more recursion. Of course, it's often used in many in computer languages. And just to bring it to the computer language that we use with the kids, we have those repeat loops that we can nest, and we can go on and on and on. So again, it's similar. So the point here being that young children, not on a meta level, but instinctively have a grasp of these concepts, of these language properties. And they will be able to use that when they come to coding, right? So this, for me as a linguist, of course, I find this fascinating, but there is another side to language and coding, and this is actually even more important here, and that is the function. So both coding and language are means of expression. And I'm first going to talk a little bit about what language does, and then show you how people, and especially children, can do the same using programming and coding. So language is a system. I just showed you some of the properties of that system, but it's not l'art pour l'art, right? It's there for something. We use it for communication. People have language for communication. And we use language to express ourselves, to be creative, and to make things happen, right? If you think about it, one of the main drivers of children learning to speak is that they can, tell people to give them something, right? So we learn language because it has a function for us. Now, expressing ourselves, there's so many different ways, but examples are maybe telling a story, describing feelings. At some point, children are able to say, I'm sad, I'm upset, I'm hungry, right? It's a sensation. There's lots of creativity. Of course, we have things like writing a poem or making a pun, but even like the sentence that I just showed you, and I could make up a new sentence, and I can come up with a sentence that no one has ever uttered or you have never heard before. That is also already creativity, right? So that we can do so much in language. And then making things happen. Making a request, giving a command. These are all things we use language. A lot of the time nowadays when we want someone to do something for us, we usually ask them, right? That's like the civilized way of doing things, mostly. So we can see that there are parallels in function. As I already said, children, we all learn language because it's useful. It's not because, it would be interesting. Let's see, why do they call this a cat? It has a function, right? It allows them to express themselves, to be creative, and to make things happen. And I will show you examples of how kids can do the same thing with coding. So we can show them that coding can have the same a function like that for them. Okay, so what are now these programming languages? You've seen some glimpses of it. Now I'm going to show you the two that we are working with. These have both been funded by the NSF and Scratch Junior, also by the Scratch Foundation. So it's wonderful to have this support for that. Okay, Kibo. This is Kibo, and I'm going to show you later on. It's okay, I'll do it. But just so that you see, this is what it looks like. And there's all kinds of accessories that I will show to you. It's a robotics kit for kids starting at 4 to 7. It uses, and I'll show that in a minute, actually, this is what you do the programming with, wooden blocks, right? So it's actually like screen-free. Natural materials for children, and it's commercially available from the Kinder Lab. And the cool thing is that children can use simple motors and sensors in the kit to create this robot that then moves and dances and sings. You can do all kinds of it with it. So in the kit, something like this, you usually have the robot body. That's the big thing there. The motors, which are in the wheels, the sensors, you have a light sensor, distance sensor, sound sensor, outputs, actually, it's not only light output, there's also sound output. And then there's something that's called a stage. We can have like a turntable on top of it, and I'll show you in a minute. There you can actually add things to it. And as I said, the programming blocks are wooden. So this is what they look like. So the idea is that in order to program, you actually stick together these programming blocks, right? So this is how you build your program. And then later on, you see there are barcodes here, and you scan them with your robot, which kids know from like grocery shopping, like the beep beep, and there's the beeping. You scan the barcodes, and then the robot will do a lot of things. So we also then show to the kids that the barcodes is the language that the robot speaks, right? The robot cannot read spin, or it doesn't understand the symbol. The robot always needs the barcode. And also, of course, these being kids, they're color-coded. So we have, as you can see, like all the blue ones are like movements. Then we have the yellow ones that have to do with sounds. And so the orange one have to do with sounds, the yellow ones have to do with light. And then we have these more fancy ones. These are where we control, for example, so until the robot comes near, it should sing. Or until it goes further away from something, it should do this or that. So there's many things that you can do with it. So you can start really simple, and we'll later show you a very simple program. Just move forward, maybe, and shake. But you can already tell just by this that there's lots of stuff that you can actually do with it. Okay. So being creative. So this is just to see how the kids integrate the robot and the stuff that they already do. You know, they try to play with toys and with props. So here I think I had to look up what it's supposed to be a cow. This is a cow. This is a dog sleigh, which I think is fantastic, right? And this is a ballerina. And I hope, now it didn't work. So the idea is that this now shows, I don't know why it doesn't do it. It worked at home, it doesn't work here. I'll try this one. Oh, why is that? Not sure. So what you would see, unfortunately, is here you would see, you see that there are all these dancers on top of the keyboard robot, and they are programmed to all move around like a dancing troupe, basically. Yeah. So maybe we can try and see together, or can see later whether I can make this happen. Actually, right? So the idea is that they can see, oh, I can do something by doing this. So this is keyboard, especially appealing to really young kids because they like also the haptic aspects of it, right? But then there's also Scratch Junior, also for young kids, usually starting around 5, we'll say. It's based on Scratch. Maybe you've heard of this. This is a program language for somewhat older kids, like 8 years and up. And it's a collaboration between our research group and the MIT Lifelong Kindergarten and the Playful Invention Company. And this is an introductory program language, but for tablet devices. So this is really a program language on screen. But of course, it's a graphical language because we all know, well, between 5 and 7, like kids' reading comprehension isn't that advanced yet. So it's something that they can do, just work with the symbols, with the pictures. You can make characters move and dance and sing, and you can edit them. You can even put your own picture in it. And actually, just to give you an idea how popular this is, and I was actually blown away when I learned this when I joined the group. So it has like 13 million users. So this is data from October, so it's already a little bit old, but we can see how many projects are created. That's 68 million different projects. People translate it, right? So the interface. And actually it's really used in almost all countries. I think one of the exceptions is North Korea, not so surprisingly. But here we can see, of course, the United States is where we have most of the users, but also a lot in the United Kingdom, a lot of the English-speaking countries, but actually also is used in other countries. And we are currently analyzing actually some interesting differences in a project one of our grad students is doing about the differences in usage in the United States and United Kingdom versus, for example, China and Japan. They show very different patterns of usage. But this is just to show you that it's really very popular, and kids and adults, teachers are interested in using it. Now, when I showed you Keyball, I showed you those blocks. This is the equivalent in Scratch Junior, right? So we have also blocks, but they're of course virtual. They're just in the tablet. You've got triggering blocks, motion blocks, then things how this is, for example, making a character grow and shrink, which is always lots of fun, and appear, disappear. You can record you can record something, so make a character say something, or sing, or add a sound effect, a crash or whatever. And then there are all these controls, where you time it, and this is where it gets actually really quite sophisticated. You can have a very sophisticated timing there, including repeat loops and so on. So just a very simple, I hope this one works now, a very simple example of creating a character and make it do something in, oops. Oh, this is too bad. I think this should be, but it should actually be in the presentation itself. This is what.
Take it out of slideshow mode and try to show it then.
I'll try that. Thank you. Well, now my computer is spaceballing. Let's wait. Okay, let's try it again. Okay, so I don't know why. It worked yesterday. Huh. Ugh. Yeah, I know. Speaking of debugging. Oh well. I don't know why it's doing this.
Are you online on a network?
Let's see. It should be Auditorium, yeah? But this should be actually embedded, so I'm not... Well, I'll wait for it to recover. Try... No? Something is happening, right? No, you see that something is happening. I'll look for it, yeah. Just give me a sec. So I think I actually have it in a smaller presentation, so maybe that will work. Maybe it's just overloaded. Let's just go back. I think I've got it in. I have another one. I might be in here. Let's see. See that one. Still doesn't do it, then I'll just give up and try later. Yeah, okay. Sorry about that. It's does anyone speak German? We call it the Vorführ effect. I know. Yeah. You want to show something, and then of course it's like, calling the technician, this doesn't work, and then he or she is there, and you're like, now it works. Okay, let's try this one. This is from the web, so maybe this works better. Maybe it was my, I shouldn't have embedded this. So this is a collaborative project with Scratch Junior. All right, so here you saw that we had, I don't know, 9 different iPads that all had Scratch Junior on it. And so they need to be timed. So for example, when you have the dragon, right? So they all need to have the dragon. Yeah, they have to share the characters. And then you have to time them in such a way that the dragon comes in after whatever 5 seconds in the second iPad, and then after 10 seconds in the third iPad, and something like this. So it's actually a great way that, and also schools and teachers do that, where they think about, okay, can you make something together? And it is complicated, but the kids actually can do this. It's really fascinating. Okay, let's go further. Nope. Okay, so now I've told you, first of all, how we think we should generally approach teaching computer science to young kids, and I've showed you 2 of the platforms that we use, the Kibo robot, which is without screen, and then Scratch Junior, which is this, it's an app that works also on Android, and one is free, where you can make things happen in that app. Now, in the last part of my talk, I'd like to introduce the Cal approach and curriculum, where we've actually taken these ideas, these concepts, and put them into concrete lesson plans and curricula for teachers to use, and have already implemented them. So this is just a quote from Marina Bears, the head of our research group, which says that as educators, we must give children one of the most powerful tools for thinking. We also say, you use that for thinking language, and both natural and artificial, i.e. programming languages. As I said before, we really think that programming is the literacy of the 21st century. And it really engages in new ways of thinking, communicating, and working with others, as you've just seen. So the Cal curriculum that we developed is centered around children's books, right? So the basis is we work with very popular children's books, and we integrate programming and literacy development. And it's available both for immersion readers and beginning readers, right? So we say like between 5 and 7, so they're just, starting, or they can already read a little bit, maybe write a little bit. And we have it both for Kibo and Scratch Junior. And for those of you who work in that area, it's maybe also important to know that it's aligned with many standards, right? If you come up with a curriculum and you want people to use it, you have to make sure that they can actually use it given the setting that they're in the school. So we have, the Common Core, and then aligned with standards in Virginia and in Massachusetts. So the structure of the curriculum is like this. It's got 12 one-hour lessons with increasingly difficult programming blocks. And the important part is that we explicitly link concepts in language and literacy with concepts in programming. And also very important is that there are lots of unplugged activities. This is something that if you work with kids, people who work with kids, they like to move around. They don't like, even if they enjoy working there, but they kind of get excited and they want to do things. So this curriculum ensures that the kids have the opportunity to move around, to do things, and that kind of speaks to their curiosity and to the energy that they have. You don't need to read all that. It's just to give you an idea of what the lessons are. And of course, it starts with, foundations, like what is a robot, or, what does a computer, and how is a computer different from an animal or a human. And then it goes on into saying, okay, what are technological tools? Then we start with sequencing, right? And then it gets increasingly complicated. We talk about cause and effect, introduce repeat loops, if statements, right? That's already quite something. And then they have final projects where they use all that, what they've learned throughout the curriculum, to make something really exciting, some exciting final project. The resources that we have for teachers are the complete curriculum, which also has lesson plans for each lesson. We have video lessons for each lesson. So the video is for the teachers, and I'll show you an example in a minute, that they know, okay, this is what I need to focus on, this is what this lesson is about, just like 2 or 3 minutes. Materials, also for these unplugged activities, for the stuff that they do outside the actual coding. And then the mastery challenges are basically just assessments to see, have the kids mastered what they were taught in the lessons and the curriculum. If you want to have a look at it, maybe you can have a quick look. It's all on this website. And if you go there, you'll see that here we have, this is the Kibo side, right? And this is the Scratch Junior side. And this is for emergent readers. And this is for readers, so kids who can already read a little bit. You can see this is like a book. There was an old lady who swallowed a fly. I'm not so familiar with all those books, but some of you are nodding, so you know that. Then Nuffle Bunny, Where the Wild Things Are, and Giraffes Can Dance. So these are the books that these things are centered around. So let's go back. Oop, where am I? I'm here. Okay. What's that?
I was just joking. Good night, you.
Yeah.
I was hoping to see good.
All right, yeah. Well, we're just getting started. We're just getting started. So just to show you the sample lesson. So this is what the teachers will see is an overview. Okay, what will students learn? What's the purpose of this activity? Purpose of this lesson? Kind of activities. Then telling what the students will be able to do after that. And of course, all the stuff preparation. What is the stuff that you need to have ready before you go into the lesson, right? And both for you as the teacher and for the students. And then here's then the activities. And you see, for example, this one starts with the dancing the hokey pokey. So this is how it starts. And then programming the hokey pokey. And it goes on like this. So this is basically the whole curriculum has all of these lesson plans and this information for the teachers. Then we also have what we call design journals, and these are basically workbooks for the kids where they, for example, we have stickers for those that represent these blocks, right? And we tell the kids, well, think about what you want to do and start planning how you want to program your keyboard to dance the hokey pokey, and they can put the stickers in. But as I said, I gave you the example with the brushing your teeth. This is another example of just from the design. It's like, how do you make a pizza? And of course, the kids are first asked to draw a pizza because they like drawing, right? You engage their curiosity and their creativity. But then you said, okay, what are the next steps for making a pizza, right? So this is again talking about the algorithm idea. So this is just to give you an idea of these design journals that we use. And here's, let's hope this one works. An example, where's my mouse? Somewhere here. Can I just play it? Of one of those videos for teachers that they can watch before they actually go into the lesson. At least it's not spaceballing, so I'm hopeful something will happen. Oh, God. This is fantastic. No? Oh, no, maybe. But I also can show you this on the website. So there's this. So wait for it here. So I think it must be this one, programming. Here we go.
Hi, welcome back to the Kibo Cow curriculum. Let's start with lesson plan 4, programming. Students will be able to tell and retell a story clearly and effectively, identify common errors with scanning Kibo programs and troubleshoot them, practice scanning programs with Kibo, and finally learn strategies for debugging and editing. In our first activity, students will refresh on the hokey pokey.
You put your left hand in and you shake it all around. You do the hokey pokey and you turn yourself around. That's what it's all about.
Then, students will end with a robot verse that will help them program their Kibo to do the hokey pokey in the next activity. In activity 2, students will program their Kibos in pairs or individually to do the hokey pokey using the Kibo blocks.
Red light on, turn left. Watch out for Kibo.
In activity 3, students will do a hokey pokey reflection. In their design journals, ask students to record their hokey pokey programs by using the Kibo stickers to write out the blocks in the program. Ask students, how many times did you use each programming block? What order did you put the blocks in? And finally, why did you choose this particular order? In activity 4, share creations, Ask the whole class to play their programs at once and dance the hokey pokey. Ask students about their challenges of programming. What problems did you have when you were scanning the blocks? Did you ever get an error message? Did you ever feel frustrated or disappointed? Why did you feel that way? In Activity 5, you'll need to go to Appendix B1 where you will find Assessment A. Good luck!
All right, so let's go back to the presentation. So this is just for teachers so that they know, okay, this is what the whole idea of the lesson is, this is why we're doing it. And here, finally, you got to see kids who were actually doing something with the Kibo robot. You saw at the end, and I mentioned that we have these Kibo mastery challenges. For example, and which program makes Kibo shake, but only if you clap, right? So it's just on one of the more advanced ones. So I don't know. What do you think? Yep, I think you're right. So this is the idea of the Kibo the Cal curriculum. As I said, it's both for Kibo and Scratch Junior. These were examples with the Kibo robot. So why does it work? So why do we think this is a great curriculum? Because it appeals to all types of students. So it's not just for the students who feel, technically inclined, but anyone, all students are creative, and it's aligned with their language and literacy development. This is why we work with those children books, and maybe if we have time at the end, I can talk a little bit more about the concepts in literacy that that are picked up in those lessons. And it really exploits children's natural curiosity and their creativity and the collaboration. They like to do things together. They can all do this. And so I'd like to contrast that again with what I showed you at the beginning, this idea of just problem solving. Nothing wrong. Problem solving is great. But this is something that really all kids love to do. And they don't get as frustrated because they can't find the one solution, because there are usually many solutions. There are many different ways you can do something. In many ways you can dance, many ways you can sing, and so on and so on. So the last 5 or 10 minutes, I'll just like to give you, show you what the group has been working on in the past year, especially the second half, and that is the implementation of that curriculum in Virginia. So probably you don't know, actually I didn't know, that Virginia is the first state that actually mandates computer science starting in kindergarten. So they said, we need to have that. We collaborated with Norfolk Public Schools, the district in Virginia. And it's a really interesting district because you've got many military-affiliated families there. And actually, this first project, what I'm now talking about, was funded by DARPA, right? So this is where it came from. The Norfolk project, so the idea is we want to explore the relationship between learning to code, computational thinking, and literacy. And it's actually like several studies starting with kindergarten, first graders and second graders, and just talking about the stuff that we've done so far, which is we started with the second graders in 8 different schools. We have students who received the Cal and controls. There was actually a little bit an issue with I'll be honest about it, with the controls, because teachers didn't want their kids to be in the control group. Right, so this is why in the end we ended up with fewer controls, and we actually a little bit behind. So we're now had to initiate like a second round of controls, basically, to make sure that we get some of the control data. So this is what we're currently analyzing, but I'll present some of that. So the duration was roughly 3 months. And what we're interested in there is, of course, the primary outcomes are this computational thinking that we've developed an assessment for, the literacy skills, and also what the educators think, and then also kids' programming knowledge and how they perceive what's going on. So far, we have results from the pre-test, so the initial stage, and some from the post-test from the treatment group, right, from the kids who actually got the curriculum. So first of all, we're very happy to find that the kids really mastered the curriculum. We have those mastery challenges, and we were really happy with the performance of the kids and that they understood this. Also interesting, so this is from the second graders. Also interesting is that we didn't find a difference between boys and girls. And we found a correlation between the initial literacy score and their success in mastering this curriculum. So we found that there is some association between literacy and coding. And it's interesting because usually, as I said, people just focus on the problem-solving aspect, right? And here we can see that kids who are good at language are also a little bit better with these kinds of activities. And then what we have right now, just from the kids who got the curriculum, we already found that it improved their computational thinking skills. If you're interested in it, I can later show you what this test look like. Basically, test of do they understand representation, do they understand modularity, and so on. And Emily Relkin, one of our grad students, has just told me yesterday that they now have some data from the delayed control group, and they didn't improve like the Cal group, so in the computational thinking aspect. And we have more data coming in, as I said, from the control group, but also from the first graders and the kindergartners, which will be exciting to implement. But so far, this was already pretty successful, especially the teachers liked it, the kids liked it. So we were really happy when in October, I think, we got the news that we received a $4 million four-year grant, this time by the Department of Education, to implement this curriculum in all the schools in the district. Right. So this was just with 8 schools, kind of a pilot to look at it. This time with Scratch Junior, so curriculum with Scratch Junior, around 7,000 children, quite a lot, 450 teachers. So this is, January is always the way it starts. We have our kickoff meeting at the end of the month. So this is something really big that we're working on, and we are very excited to bring this to all those schools in the district. Okay. Just to wrap up, computational thinking and coding are fundamental skills for the 21st century. They're not just there for computer scientists, and they're not just there to make sure we have a competitive workforce. Children as young as 4 years can actually learn to code. It's something for us. Most of us probably have learned to code. I know I did in college, right? Something pretty astonishing to know that kids can do that. Traditional approaches, as I showed you, usually focus on problem solving. Our approach is to get children interested. We really need to link those computational thinking concepts to everyday life. We need to integrate coding and language and literacy development and allow children to use this for self-expression and creativity. Thank you.
I think we're still waiting for a pizza.
Correct.
That's good. I can maybe show you, or you can ask questions.
Yeah, we want to see.
Yeah, okay. I'm not. I have to say.
Turn on the light. Oh,
Yeah. Thank you.
Yeah, that's right.
Okay. So let's start. This is, I hope at least this one works now. So as I said, we always need to start with something the kids learn with a begin, right? So with a begin block, and we could maybe just start with something move forward and shake, right? And then where is it? We need we need an end block.
Maybe we can.
Oh yes, let's do it on the table. Great idea. Let's do that. All right. So.
Oh, here it is.
All right. Okay, so I'm not a keyboard expert, but I'll do my best. So is it already? Oh no, it's still playing. Is it already? Oh, come on. Ugh. The grad students who work on this project are experts in scanning. And I've done that like 4 times, and I'm still working on it. Come on. Yeah, so and I can't put in the number like in the grocery store. I actually need to use the barcode. Oh, come on.
So you definitely need the sequence
Yeah.
in this effort.
Yeah.
So you guys didn't consider doing like an RF signal for proximity for people
That
that,
would-
have issues with fine motor skill.
That's a really good point. No, at this point, it's really just working with that. Yeah. So let's see. So now the idea is it's programmed. It's stuck. Oh, come on. Do it again.
maybe have it
Yeah.
start.
Let's try it again.
Wise.
Yeah. Start again. But now it wants to scan again. This is not good. Let's start again. Okay. I should have brought one of the RAs with me who are the scanning experts. Maybe I shouldn't. This is why I don't work at a grocery store.
You put it over here.
Okay. Has it? Why is it not? There you go. That's okay. That's the basic idea, right? Yay, finally. But it can actually, where's the, oh yeah, here's the kit. So we can actually add things. So for example, we can say, yeah, I wanted to shake, but only after I've clapped, right? So I could say, that's a little ear, yes. So they learn about that. So let's start again. I hope this doesn't work.
Oh, you can so much better.
Yeah, let's see. Is it not doing it? No, that's later. It should first move forward. Oh God, let's try again. It should, once it gets the end, it should just turn green.
It's green.
Okay. But it's still trying to scan. That's weird. Okay. There we go. Right. And you can do all kinds of things. You can add a red light, you know, can turn. But then, of course, you've got these more sophisticated things, just like repeat, right? And you can, and here you see you've got this little felt, what do you call that? And Velcro. And with the Velcro, you can then add what you want to have, right? So maybe you say repeat 3 times, right? And things like that. And so, yeah, it says until near, as you said, like with a sensor. In that case, the sensor, you can use the sensor, for example, say, oh, I wanted to shake until I come near it, and then I wanted to freeze, for example. So I can do things like that. So, yeah, so this is the Kibo robot, and this is the what I told you about, this little stage that you saw in the videos that didn't work, and I'll see if I can get them to work maybe now, where kids can put things on top to make it more like, I don't know, an animal or something along those lines, right? They really like that. Yeah, so that's the idea. But now I interrupted someone who wanted to probably ask a question. You had already a question, or?
I got several.
Yeah. Okay.
Yeah, let's have someone who is not staying here for lunch.
Yeah.
To ask us one more question, and everybody is welcome to stay for lunch, and then we will discuss more after everybody gets their pizza and sit around. Right? So we have one question.
First question. This is a very simple question, so maybe we can start that. How does it work for children who don't read? Do you tell them the meaning and then they try it, or do they try it and discover the meaning?
They work with the symbols mostly.
Yeah.
Right? Yeah.
So if it isn't obvious, like, do you let them
Yeah,
do it first,
yes.
or do you tell them first?
Usually it's finding out by trying it, right? I mean, sometimes when they're stuck, you can then say, okay, well, let's try. But usually, let's try it out. Let's see what happens.
Okay.
So you want to kind of ask them to use their observational skills to kind of make the connection, right? Yeah.
I think you have to get over the idea of language being spoken. There's pictorial, there's tactile, there's gesturing, there's sign.
Yeah.
And this is a means to that end, by visual clues.
Yeah. It's interesting because us as adults, we kind of read, we can't stop ourselves from reading. So I don't know. It would be actually.
And you're doing left to right. What about the right to left people?
Oh, absolutely, absolutely. I mean, here's the thing: you can actually, they don't even have to be connected, right? So. It should work this way too. If I just put them that way, And actually, at some point, and I had to learn that. It's like sometimes you're like, oh no, I need another backwards thing, and then you learn, oh, I can just scan it twice. Right. Because the keyboard doesn't know how many blocks there are. It's just waiting for the input with the scanner, right? Yeah. You're all hungry?
Have you tried this out I'll start my questions, and I'm glad that you are actually prototyping this in a community that has a lot of military, because that would help broaden the range across cultural, historical, socioeconomic status, because if anything, that's one of the more diverse workforces. Have you shown studies between lower socioeconomic classes of folks with those that are more enabled, and have you thought about integrating this in inner cities?
I think
where there's lower socioeconomic status, where they're more equipment poor. And the follow-up question to that is, what prior exposure to technology in this lower age group, in this community in Virginia, did they have prior to the introduction of this, to see what was familiar?
No, I mean they are. I mean all of the kids, as far as I know, are familiar with smartphones nowadays, right? So, but this is.
But it wasn't encouraged necessarily in the classroom.
No.
So
So
like
there was
several have like
no
one-to-one devices and all that.
No,
that
there was
effort
no
wasn't there.
prerequisite. And even the idea was that the teachers done that, right? Because the teachers were being trained by us how to do this. So we had like professional development workshops, but also virtual coachings and so on. But to come to your question about the socioeconomic stage is really interesting. So at this point, I'd say we're doing this in Virginia because this is a more challenging environment. There's lots of fluctuation, for example, people move about and so on. Also lots of kids who don't have English as their first language and so on. So we are also, part of the study will be to see what influence does that have, that they maybe are not native speakers. All I can say is that all of the piloting was of course done at Tufts, and then the kind of the area that is like Medford, Somerville, Boston, Cambridge. So yeah, you get the professor kids coming to do that. But this is why we're actually so happy to then see that this translated so well into this different into this kind of different environment. But we haven't explicitly studied that. Right? This is really the very beginning.
Well, with that high end number, you should be able to get something.
Yeah, we will actually. This is a good point. With this one, we will have some information about the difference in SES in the different schools. So we will try to see if we can find proxies to work with that. Coming to the cross-cultural part, this is a really good point. There's currently another project going on in our group, which is something that you probably wouldn't expect. It's about religion. And there are schools. We have Catholic school, Islamic school, we have Jewish school, and non-denominational, and in Germany, in the US and in Argentina. And they all work on, they use the curriculum to learn something about values in the different faith systems, and then they work together. I'm not on that project, but here's already we're looking at differences. Do maybe the Argentinian teachers approach it differently from the American teachers and so on. So this is the kind of stuff that we're currently working on to find out more about this. Yeah. Sorry. Let's have the things I get cold.
Yeah, but you get up first.
Let's have Laura have for lunch.
Okay, you can make a question.
Yeah, but Laura, can we play with this? Well,
yes, sure.
Not too much research though.
We have several of those.
For curious and you can experiment this. But also,
Thank you so much. Thank you.
So let's get some pizza.
Right.
We have more discussion later.
Oh, that's perfect. Thanks so much. Yeah, because I don't need to. I agree.